Okay, so this is going to be the conclusion of the quiz on 2.3 through 2.5. So this is the back side where we had a question about position, velocity, acceleration, and speed, and then also a question about tangent lines. Number 4 was the question about position, velocity, acceleration, and speed. We're told that this formula right here represents the position of an object as it moves along a straight line at time t. We want to find formulas for velocity and acceleration, and then we want to use them to try to decide if the speed of the object is increasing or decreasing when t is equal to 2. So here's my position function, just rewritten without a radical, so I rewrote it in exponential notation. The derivative of velocity, or the derivative of position, excuse me, is velocity. So rate of change of position is velocity, so I'm taking the derivative of that position to develop my velocity formula. I used the chain rule here. A handful of people forgot to use the chain rule on the quiz. I said I don't really need you to show you simplifying a derivative unless you're using that derivative to do something, and we're going to use this derivative to take another derivative, so it's going to be worth 10 seconds to think about how this simplifies. We have a product of 3 different pieces here. The 1/2 and the 4, easy to take the product of. 1/2 of 4 is 2. So before I take another derivative, because I'm looking for an acceleration function as well, I'm just going to multiply these together, make it look a little cleaner. So here would be my slightly more simple velocity formula. I'm going to go ahead and use this to take another derivative. The second derivative of position would be acceleration, or the rate of change of velocity would be acceleration. So the derivative of this is going to require the chain rule because I have an outer function 2 something to the negative 1/2. So I'm going to do the derivative by multiplying this by the exponent, and 2 times negative 1/2 is going to be negative 1. And then I'm going to have to subtract 1 from this exponent. It's going to become a negative 3/2. Sorry about that, kind of sloppy in my exponent there. It's a negative 3/2. And then the inner function is going to stay inside this quantity, so 4t plus 1. And then I'm going to multiply by the derivative of my inner function, and the derivative of my inner function is 4. I want to use what we just developed to find the acceleration at 2, the velocity at 2, and then try to determine what's happening with speed of this object at 2. Since I'm going to put 2 in place of this t and evaluate, and in place of this t and evaluate, I'm going to simplify further because I don't like plugging in values when I have negative exponents. So I'm going to move this across the fraction bar into the denominator. So I'm going to have 2 over 4t plus 1 to the 1/2 power. And hopefully you recognize that as a square root in the denominator. And similarly, I have a negative 1 and a 4. I can multiply those together, put them in the numerator, and then in my denominator I'm going to have 4t plus 1, and I've moved it to the denominator so I'll be able to change the sign on this exponent to a positive 3/2. I want to know what v of 2 is. I want to know what a of 2 is. So for v of 2, I'm putting a 2 in place of t and I'm evaluating. So I'm looking at the 2 in the numerator over 4 times 2 plus 1 raised to the 1/2 power, or all under a square root. That'd be 8 plus 1, so that'd be a 9. So I'd have 2 over square root of 9, or 2/3 for my instantaneous velocity at 2. My acceleration at 2 is going to amount to me putting 2 in place of this t and evaluating. And this is where, if people made it this far correctly, where we started to go wrong a little bit. And it's basically just an algebra issue. You can rewrite this expression here as the square root, because this denominator in the exponent represents the index on the radical, and I can raise that square root to the 3rd power. So it's a square root that's being cubed. So I'm going to have the square root of, oops, that's a 4 times a 2, my fault. 4 times 2 plus 1. So I put the 2 in place, I put the square root there, and then I'm going to have that square root being cubed. And if you continue to evaluate, you know, this is basically what we evaluated a few seconds back. That's a 9 underneath the square root. And the square root of 9 would be a 3. 3, whoops, not 3 squared, but 3 cubed, right? That exponent would be a cube. Would leave us with 27 in the denominator, -4 in the numerator. So here's your velocity, here's your acceleration. What does this tell you about speed? Well, think about the velocity graph. Speed is equal to the absolute value of velocity. So if velocity is getting closer to 0, your speed will be decreasing because the absolute value of velocity will be decreasing. If your velocity is moving away from 0, your speed will be increasing because the absolute value of velocity would then be increasing. So I'm going to think about the velocity graph. So if this is a graph of velocity, I'm trying to determine at the value where t is 2, what's happening with my velocity. Is it moving closer to 0? Is it moving farther from 0? So at 2, I know my velocity is 2/3. So I'm just going to try to plot a point on my velocity graph of 2, 2/3. This is the derivative of velocity. And graphically, a derivative represents the slope of a tangent line. So the slope of my tangent line at this point has to be -4/27. So I'm just trying to draw something that would have a very tiny negative slope. So I drew that little component of the velocity graph in. And if you look at what's happening with this velocity graph as we go through the point where t is 2, isn't that velocity getting closer to 0? So since this velocity is getting closer to 0, the absolute value of velocity is decreasing, and hence speed would be decreasing. And then the last question here was a tangent line question. I've already rewritten the function so that's going to be easier to take the derivative of. And you're going to find the slope of your tangent line by evaluating your derivative at the value you want the tangent line at. So it's going to be at x equals 1. But I need the derivative first. So I'm going to go ahead and multiply by my -2, subtract 1 from it. I'm going to do this coefficient times that exponent, and that'll give me a -1. And then I'm going to subtract 1 from that exponent. So the derivative we didn't have much of an issue with. What we had an issue with was evaluating this derivative at 1. I'm evaluating this derivative. I don't like the negative exponent. So I'm going to go ahead and I'm going to do a little bit of simplification before I try to put 1 in place of the x's. So f prime of x is going to be able to be rewritten as, this is 2 separate terms. This has a negative exponent, that has a negative exponent. Because I have 2 separate terms, I'm going to rewrite this with 2 separate fractions. -2 can stay in the numerator of the first one, but the x is going to move across into the denominator, and I'll change the sign on its exponent. And similarly, I want to move this to the denominator, so it's going to be x to the 1/2, or you can think of it as a square root of x as well. I'll write it as x to the positive 1/2. Okay? We want to evaluate this at 1. So I'm going to put 1 into my derivative. F prime of 1 is going to end up being -2 over 1 cubed, which is just 1, minus 1 over the square root of 1, which is just 1. So we have -2 minus 1, or -3 for the slope. A handful of people stopped here, and I kept pointing this out in class. If you're asked for the equation of a tangent line, calculus gets you the slope of the tangent line. We know the slope of our tangent line is -3, but if we want the equation of a tangent line, we need our answer to either be in point slope form or slope intercept form. I need to know a point on this tangent line in order to develop that tangent line's equation. So I know that the x-coordinate of the point of tangency is 1. I can figure out the y-coordinate of the point of tangency pretty easily. Point of tangency is going to be 1, f of 1. If you try to evaluate f of 1, what do you end up with? Well, let's see, we're going to end up with 1 over 1 squared minus 2 times the square root of 1. And let's see, this would simplify to what? 1 minus 2? 1 minus 2 would take us to -1. So we just need to wrap things up by writing out the equation of a line that has this as its slope and goes through this point. I'm going to go to point slope form. So I'm going to have y minus y1, which is -1, so plus 1, equals m, which is -3, times the quantity x minus x1. If you went to slope intercept form, that was also fine. but there's the equation of your tangent line.